chapter is alternating current. 11.1 is sinusoidal current. That means the currents follow the sine graph. As you can see the graph below, it is a sine graph. Okay, this is a sine graph. And then first we have to understand some of the term here. We start with period. So period is the time from here to here, maximum to maximum. Or you can take minimum to minimum. Or the other way is you can take from origin to here. This is also period. Okay, so the time for one complete cycle of the alternating current, frequency f, number of oscillations per unit time. So where frequency is 1 over period, peak value, I naught or V naught, highest point on the graph. So that means, we have two possible graphs here, either current versus time or potential difference versus time. Okay, so no matter which graph, right? So the highest point is here, then you bring it to the side, then you will get either I naught or V naught, the peak value. Okay, so it's the maximum value. And here, instantaneous current or voltage, I or V, the current or voltage at a particular instant. So that means you can look at the graph. Let's say you want to find when the time is 1 second, what is the current? Then you have to do here. Let's say this is 1 second. You bring it up, then you bring it to the side, then you read the current. That is the instantaneous current. Okay, so instantaneous voltage should be similar. So where you have to look at the time, then you bring it to the y-axis to read the value. So of course the alternative is you can use the formula here. Okay, this formula, I equal to I naught sine omega t. So I equal to I naught. I naught is where it affect the amplitude. Okay, the maximum I affect the amplitude. And sine omega, this part will affect the period. Okay, this part will affect the period. So multiply with time. So the omega here, which is last time known as angular speed. So over here, the formula is omega equal to 2 pi f. 2 pi f. Okay, so of course we have another version under the voltage version. So V equal to V naught sine omega t. If the graph is sine graph, then you can use this. And then the omega is again 2 pi f. Okay, so how to use these two formula? So let's say one example. Okay, so I draw on the screen. Let's say they give you a graph of I versus t. Then they give you a graph like this. Let's say this is 1 second, 2 seconds. So the time is in second. The current is in ampere. And let's say this is 3 ampere. Okay, so what we can do is we use the formula I naught sine omega t. So the I naught is 3. The omega is 2 pi f. So 2 pi f. F is frequency. Frequency is 1 over period. So we know that the period is here all the way to here. So the period is 2 seconds. 2 pi times 1 over 2 t. Okay, then we will get the equation 3 sine pi t. 3 sine pi t. Okay, so once you get the equation, of course you can use it to find instantaneous current or instantaneous voltage if you are finding out the voltage equation. So for example, let's say I want to find instantaneous current, I can do it like this. Let's say for example the question asks when when t equal to, let's say when t equal to 3.5 seconds, I equal to what? This is instantaneous current, and at that particular time. So I equal to 3 sine pi times 3.5. Okay, then after that, we just need to make use of calculator. 3 sine 3.5 times pi. Then we get -3. So meaning that this is the instantaneous current. Okay, so of course, for v equal to v naught sine omega t, we can use this if the graph is v versus time. Okay, so since it is just similar, so I just assume you know how to do it. Okay, now this point, the root mean square RMS value. Root mean square value. What is that root mean square? So we have two types of root mean square value. Root mean square current or root mean square voltage. So it's the value of steady current or voltage that produces same power in a resistor as the alternating current or voltage. Okay, so that means what? That means, let's say example, if you are using alternating current and you pass through an electrical device, and after that, let's say the power is P. The power is P. The power is P, yeah? Okay, so the power of this electrical device is P. So this power P, right, is actually, P equal to VI, right? Okay, so the problem is in alternating current and alternating voltage, the value is going up and down. So it's here, then go up, then go down, then go up again, and so on. So which value should we use for their voltage and for their current? Okay, so we can't take maximum because it is not always maximum. It's just maximum for one particular moment only. After that, they go down to zero, then go down to this minimum. So taking maximum is not reasonable. Or maybe you feel like, oh, if not reasonable, then I take average. If you take average, the average value will be zero, So because they have maximum here, then they have minimum here, in average is zero. Okay? So taking zero is not reasonable also, because if you connect an alternating current to an electrical device, the electrical device have power, so it cannot have zero power. So taking mean is not a problem. It is not reasonable as well. So because of that, we have to take root mean square. We have to take root mean square value. So meaning that the power that the electrical device receive is the power when you take the root mean square voltage multiply with the root mean square current. Okay, so which means you have to take root mean square voltage multiply with root mean square current. Then the power that you get is called mean power. Sorry, average power. Average power. Okay, so what is root mean square voltage and root mean square current? We take this formula. We take the I naught divided by square root 2, and on the other side, we take the V0 divided by square root 2, then we'll get the root mean square value. Okay, so root mean square value is something like the effective value. The effective value, you know, they are like going up and down. Effectively, how much current is providing, or how much voltage is provided by the alternating current. So you can count that out by using root mean square value. So imagine we use the formula and it becomes this. Then you get V naught I naught over 2. So this is the average power. Okay, now let's move on. 11.2, mean power in an alternating current supply. For a sinusoidal alternating current, peak power is twice the average power. So let's see what is peak power. Peak power, right, is maximum power. So you want to get maximum power, you take maximum voltage multiply with maximum current, and then you will get peak power. So if you compare these two, you will realize peak power is double of average power. So that's why we have this statement here. Peak power is twice the average power, as you can see here and here. Okay, now power equal to I times V. So the I and V, you have to use root mean square value, and you substitute, and then you get something like this. Of course, the working is already here. It's the same thing. It's just that this I and V have to put I naught V naught. Okay, now let's see one question here. An alternating voltage is represented by the equation V equal to that value. For this alternating voltage, determine peak voltage. Okay, so peak voltage is the front part, 220. Peak voltage. Peak voltage means V naught. So it's 220 volt. The root mean square voltage, the formula is equal to V naught over sub 2. So it's 220 over square root 2 equal to 156 volt. The frequency you have to take it from here. You have to know that this whole part is omega. So the working, let's say I put here, omega equal to 2 pi f, and omega is 120 pi, 2 pi f. Then f is hence 60. Then we put the unit 60 hertz. Okay, so let's move on. This side. Okay, so we have the next subtopic, and let's go through first. 11.3, transformer. So transformer, let's see, the first point. Device used to increase or decrease the current or voltage of an alternating current. So this is the function of transformer. It is to increase or decrease the voltage, and at the same time the alternating current will just change accordingly also. How they change is like, if the voltage increase, the alternating current will decrease. If the voltage decrease, then the alternating current will increase. Okay, so in opposite relationship. Now let's see the second point. They say ideal transformer. So ideal transformer means the perfect transformer. No power loss in the transformer. The input power is equal to the output power. So input power, of course, first of all, you have to know that the formula of power, as we discussed just now, power equal to Vi. And input power is the power on the left hand side. We take the IP and the VP. IP means the current in the primary coil. VP, the voltage in the primary coil. This side is primary coil. Okay, so the input power is hence IP VP. The output power is the right hand side, where you have to look at the secondary coil, look at the current and the voltage, secondary current, secondary voltage, multiply each other, then you get the output power. Okay, so we get IP VP equal to IS VS. Okay, so based on this formula, we can easily understand one situation. Let's say if you increase the Vs, then the Is will decrease. If you decrease the Vs, then the Is will increase, provided that each side is left hand side is constant. So the changes is in the opposite situation. Okay, so the other thing is you can also see NP and NS. NP is how many turns in the primary coil, and then NS is how many turns in the secondary coil. Okay, so now let's see the information after this. The first point here, the potential difference Vp across the primary coil causes an alternating current IP to flow, producing a magnetic field in the soft iron core. Okay, so that means first your Vp has to be alternating current. Then because this is alternating, then your IP is also alternating. Okay, so they are alternating current, and then they enter the primary coil, and this primary coil produce a magnetic field. Okay, so produce magnetic field. Imagine how you see the current come in, then they turn. Let's say they turn this way. Okay, I put arrow. Let's say they turn this way. And then they come out. So when they turn that way, right? So what to do is you have to know that it produces a magnetic field. This magnetic field, you want to know the north pole and south pole, you have to use right hand grip rule. So imagine that right hand grip rule, the forefinger that you grip, right, that you twist, right, must follow the direction of the current. Okay, so in front they are going this way, and at the back they are going to the right. So you have to twist in a way such that your thumb is pointing down, so showing that the north pole is down here, the south pole is up here. So it produces an electromagnet which is like this. And the electromagnet will just cut the secondary coil, and then they go back to the south pole. So when they cut the secondary coil, then the secondary coil will induce EMF. So meaning that they will have voltage in the secondary coil. Okay, so then because of that, because of the presence of the voltage, and then they will have the current that move also. Okay, so after a while, alternating current, as you can see, there will be positive. After a while, it will be negative. When it is negative, that means, let's say I use blue color. That means the current will enter from this side, then they make a round, then they will go this way, opposite way, then they come out from here. Okay, so after a while, they will follow the blue color arrow. So everything is in the opposite way, and we use right hand grip rule. You will realize that the north pole is up here, the south pole is here, then the magnetic field is the other way around. Okay, so let's say I route away the IPVP and the ISVS. Okay, so will be the other way around in this way. North pole, they come out. South pole, they go in. Okay, so they come out. They cut the secondary coil, and then they go in back to the South Pole. So what we can see here is when they cut the secondary coil in the second round, they cut in a different way, opposite. So because of that, you should expect the IS and the VS will be in the opposite direction also. So meaning that the IS and VS should be the alternating current and the alternating voltage also. Okay, so and this process keep continue, you know. After blue color, then they change back to red color. Then they form magnetic field and cut again. Then they change to blue color, then they cut again. And they keep cutting the secondary coil again and again, and then they keep generating alternating current at the secondary circuit. Okay, so that is how it works. And then let's move on. Okay, next point. The secondary coil is thus in a changing magnetic field. As what I mentioned just now, start from the red color magnetic field, then followed by the blue color magnetic field that keep changing. And an alternating current IS is induced in it, producing an alternating EMF VS across the secondary coil. Okay, so this one we discussed already. And we have two types of transformer, which is step-up transformer, where the primary coil has fewer turns than secondary coil. Hence, output voltage is greater. Current decreases by the same factor. So it means if you have step-up transformer, the NP is smaller, the NS is larger. You have more turns on the right hand side. And then the voltage here will be larger. Okay, will be larger also. Of course, there is a formula. There is a formula which is like this. They follow ratio. NS over NP equal to VS over VP. And they follow ratio. Okay, so if they are many times greater, let's say NS is many times greater than NP, then VS will be many times greater than VP also. So it will be it will stack up a lot. Okay, so this is a stack up transformer. And the other thing is the information here also mentioned the output voltage is greater, VS is greater, but the current will decrease by the same factor. So how it works, imagine that we have this formula, IPVP equal to ISVS. From this formula, if I rearrange it, VSVP is equal to IPIS. And this formula, you put it down here, then it will become IP over IS. So meaning that current is the other way around, IPIS. You see, this is secondary on top, primary at the bottom. But current is the other way around. And hence the changes is the other way around also. If voltage increase, then current will decrease by the same factor. Okay, now let's see step down. Step down transformer. Primary coil has greater turns than secondary coil. Hence output voltage lower. Current increases by the same factor. So that means step down transformer is the other way around. The NP is greater, the NS is smaller. So this is smaller, the bottom one is greater. And because of that, here we change in the same ratio. Vs is smaller, Vp is greater. But the current is the other way around. The IP, so the IP is smaller and the IS is greater. So that's why current increase, but voltage decrease. Okay, so we finish up this place. Okay, so on this page you can see the formula that I mentioned just now. So first we have IPVP equal to ISVS. That means the input power equal to the output power. And the second formula I also discussed already. Okay, so the secondary for NSVS is at the same side, but for current it is at the bottom. NPVP at the bottom, but IP on top. Okay, so let's move on first. 11.4. Phase difference in VP or VS and IP, IS or phi. Phi is the magnetic field. Okay, the magnetic field. So now let's see the first point here. The alternating current in the primary coil is not in phase with the alternating EMF induced in the secondary coil. It's not in phase. Okay, so which two are not in phase? So let's see. Alternating current in the primary coil. This is IP. IP. It's not in phase with the alternating EMF induced in the secondary coil. This one is VS. Okay, so IP and VS, they are not in phase. So what is meant by not in phase? So let's say example. If your IP is the red color graph like this, okay, let's say the red one is IP. Here is I or V lah, let's say. This is T. Then your VS, right, which is not in phase. The graph, it looks different. Okay, and what is meant by this is the VS graph will start later. As you can see, the red graph start from origin at time equal to 0, but the blue graph start from the horizontal axis, slightly later. Okay, slightly later. How much later? You know, here to here is 90 degree. They are 90 degree later. They have a phase difference of 90 degree. As you can see the last point here. Phase difference of 90 degree. We look at the last point first. Let's see what are they talking about. VP and VS have a phase difference of 90 degree with IS, IP, and phi. So that means this set has a phase difference of 90 degree with this set. Okay, so they have a phase difference of 90 degree. As what I show here. Okay, this first point is matched with what they said here. The IP, which is this one, IP, compare with the VS. So they have a phase difference of 90 degree. Likewise, IS and VP also have 90 degree. IS, VS also 90 degree. VP, IP also 90 degree. Phi and VS also 90 degree. Phi and VP also 90 degree. So as long as they are one from here and another one from here, they will have a phase difference of 90 degree. But if they are from the same group, let's say IP and phi, how much phase difference? No phase difference. No phase difference means their graph looks the same. Both have sine graph. Okay, so if let's say VP and VS, what's the phase difference? No phase difference. Okay, so let's see more information. Current in primary coil give rise to magnetic field. This one we discussed already. The current in primary coil, that is IP. So the functions of IP that enter the primary coil is to produce magnetic field, and then the magnetic field will cut the secondary coil, right? So you see the next point. The magnetic field in the core is in phase with current in the primary coil. So they are trying to say that the magnetic field is phi and current in primary coil is IP. The phase difference is 0 degree. So they are saying this. Compared with this one, they are saying that IP and VS, the phase difference is 90 degree. So this match with what I mentioned also. Phi and IP, they are under the same group. Same group, no phase difference. The magnetic flux cut the secondary coil, inducing EMF in the secondary coil. The EMF induced proportional to the rate of change of field, so not in phase. So what are they talking about? So let's say I give one example here. This point is about Faraday Law. EMF induced is a Vs. Is proportional to the rate of change of field. dn phi over dt. Faraday Law. So not in phase. This formula will explain why they are not in phase. Okay, so Vs and phi is not in phase. You see, Vs is here, phi is there. They are not in phase. They have a phase difference of 90 degree. Basically because there is a differentiation involved here. Imagine that if your phi is a sine graph, then you have to differentiate the sine and it becomes cos, So your Vs will be a cos graph. Okay, so it's something like that. So that's why there is a phase difference of 90 degree. The sine graph, after differentiation, it becomes cos graph. Then because of that, there is a phase difference. So at the end, what to remember is, just remember these two has a phase difference of 90 degree with these three. Must memorize. Okay, must memorize. And let's move on first. We haven't finished transformer yet. 11.5 eddy current. So what is eddy current? You try to imagine. This is your transformer. And we have primary coil here. Then we have the secondary coil here. Then just now what I mentioned is it produces magnetic field. Then the magnetic field cut the secondary coil. So they cut the secondary coil and induce EMF in the secondary coil. Then they come back to the primary. So when they cut the secondary coil, right, EMF is induced. But the problem is they also cut the soft iron core. This is the soft iron core. When the magnetic field cut the soft iron core, it induced EMF also. So because of that, there are currents that flow around the core. So if you are wondering is whether the current can go into the secondary coil or not, actually cannot. The current in the soft iron core, they can only move around here. They cannot go into the primary coil or the secondary coil because the wire is covered with insulator. It's covered with rubber, let's say, for example. So they are not connected straight away with the soft iron core. Soft iron core, somehow it is laminated, it's covered by plastic. Then the wire is covered by plastic also, or by rubber also. So they are not, the current in the soft iron core cannot reach the coil. So this blue color current is induced, and there is nowhere to flow. They may just flow around, okay, in all kind of way, and this is called eddy current. Eddy current. Eddy current is the current that flow in the soft iron core. The current that flow in the secondary coil is called IS. We don't call it eddy current. So then what is eddy current? Eddy current is the current that is not intended to induce. Our primary purpose of doing this transformer is to induce EMF in the secondary coil, not in the soft iron core. But somehow it happens also. EMF still induced in the soft iron core, and this current is wasted, because it's not used to make the electrical device work. Our electrical device is connected to the secondary coil. Okay, so wasted one. So it make power loss happen, or energy loss as heat happens. As you have to imagine, they have nowhere to go. They keep moving around here, and let's say the soft iron core has resistance, and then they will make energy loss as heat. So that is eddy current. So if a metallic conductor moves in a magnetic field, and EMF is induced, which will make free electron in the metal move, causing electric current. Okay, so they are trying to tell you something basic. You have magnetic field, you have conductor, you have a metal, then you make the metal cut the magnetic field, then they will induce EMF. Then the free electron will move to form an electric current. And if the electric current form is in the secondary coil, we don't call it eddy current, we just call it secondary current. But if the eddy current form is in the soft iron core, then we just call it eddy currents. The eddy current will oppose change in flux linkage of the conductor by Lenz's law. and energy of motion will be dissipated as heat. Okay, so this eddy current, of course, it causes two problems. It causes change in flux linkage to be more difficult because it's opposing it, and then it causes heat loss, okay, and energy loss as heat. So these are the bad part of eddy current. Okay, so now let's look at 11.6. Energy loss in a practical transformer. Like what we discussed, energy loss because of eddy current. But it is not just eddy current that contribute to energy loss. We have other factors also. Some power is lost due to resistance in the coil of transformer, causing them to heat up. So like the primary current want to enter here, but the coil has resistance, and then heat loss as heat. I mean energy loss as heat. Some power is lost as the magnetic flux flow back and forth. Okay, so imagine the primary coil will form magnetic field. After a while, the magnetic field will form in the opposite way. And these formations of magnetic field in different directions causes power loss. And to minimize this, a soft magnetic material is used where magnetic flux direction can change easily. Okay, so meaning that you can put a soft iron core inside, then it will make it change more easily. Okay, but soft iron core has its weakness also, like it induces eddy current, that is another problem. The good thing is the soft iron core will make the magnetic field change more easily. Yeah. So next point, losses also occurs in the core due to eddy current. Now, this one I discussed already, the current in the soft iron core. And then induced current flows through the iron core and dissipates energy due to its resistance. That means energy loss as heat. Current can be reduced by, eddy current. Eddy current can be reduced by making core out of thin laminated sheets. Okay, what is that? That means when you build up your soft iron core, right? Instead of using one big piece of soft iron like this, we have an option of using many thin sheets of soft iron like this, many layers. Each layer is laminated. So laminated means you cover it with plastic. By doing so, right, your soft iron core, which is many layers of plastic, many layer with thin iron sheet, and each thin iron sheet is covered with plastic. So if this happens, then eddy current can be minimized. So over here, flux can easily flow. That means the magnetic field. But eddy, flux, like what they mentioned here, with the soft iron core, then the magnetic flux direction can change easily. So although you are using laminated sheet, but still the soft iron core is there, so that's why the magnetic field can change easily. Eddy currents cannot. That means we minimize the eddy current induced. So let's move on. Okay, this part 11.7, transmissions of electrical energy. Okay, what it means by this part is, imagine electricity is generated in a jungle, in a rural area, by using hydroelectric. Okay, so after electricity is generated in the jungle or the rural area or the dam, then the electricity have to send to the city area, which use up a lot of electricity, and they have to send the electricity through cables or wires, and that is called transmission of electricity or transmission of electrical energy. So it is through cable. So over here, what happened is electricity transmission lines have resistance. That means the cable have resistance. And some more it's very long, from rural area to city, so they have to travel a long journey. Therefore, energy will be lost through heating in the wires. So energy loss. Okay, so we don't want that to happen, or else generating electricity is just waste of time and waste of energy. So at the end, energy loss. So we want to minimize it. Although we cannot put it into zero, but we still able to minimize it. Okay, so what to do is electricity transmitted at high voltage, alternating current supply. So we want to avoid energy loss, or we want to minimize energy loss, then we can use step-up transformer. A step-up transformer will increase the voltage. Okay, will increase the voltage. At the same time, the output voltage is still alternating voltage. Okay, it's still alternating. So why you have to increase the voltage, and why you have to use alternating current supply? So of course, alternating current supply is compulsory for transformer lah. Transformer must use alternating current. Okay, direct current doesn't work in transformer because imagine if you are using direct current. So what happens is the current will just flow in one direction all the time and then flow out here, let's say lah, and then they form magnetic field. So the magnetic field will just cut the secondary coil when you turn on the direct current. They cut one time only. Cut one time only. Then your electrical device will have EMF induced for a very short period of time only. When you turn on, then they have EMF induced. After that, no more EMF induced already. So why there is no more? Because the magnetic field cut one time only. After that, no change already. EMF is induced if you keep changing the cut of the secondary coil. If you don't change it, it will cut one time. So alternating current works here because after a while, then the magnetic field will form in the opposite direction and cut again. Then they will form in this direction and cut again in the different way. So they keep cutting the secondary coil non-stop one. Okay, so in different way lah. In that situation, EMF is induced. So that's why we must use alternating current in transformer. Direct current cannot. Then why we need to use high voltage? Our formula VPIP equal to VSIS. So if you use high voltage, you use step-up transformer to make the voltage high, the output voltage high, then the current will be low. Then after that, they said current is smaller. This one is smaller. So less heating and voltage loss in cables or wires. We know that power loss is I square R due to the resistance in the cable or the wires. So since the IS is small, then the power loss is small also. Okay, so that is why we need to use high voltage so that the current is decreased, then the power loss is decreased also. Okay, so imagine what happens is you use high voltage to send it from the jungle to the city. When they reach the city, right, they need to use step down transformer to make the voltage back to a suitable value, to lower down the voltage. We can't use high voltage all the time, as it is dangerous. Imagine in city there are human beings here and there, so with high voltage, maybe you get electric shock easily. Imagine you're making a handphone call, then the high voltage may make something like lightning happen, so the the high voltage make the electricity like strike you, so something like that can happen. So it is not safe to use high voltage in the city. So you have to step down. You have to use step down transformer to change it back to low voltage when they reach the city. Okay, so now, okay, this is all about transformer. So transformer finished already. Okay, so you see the process already. From the point where electricity is generated. Electricity is generated by using uh, EMF induced that we learned in the previous chapter. So it is where you have to use a magnet and the conductor that cut. Okay, so the basic concept is it's something like this, You use a magnet, north and south, then a coil. Okay, so then you move it in and out, where they follow Lenz's law or Faraday law. So you move in and out, then it generate EMF is induced. And the EMF induced is alternating current because you are moving in and out. Okay, so alternating current is generated. And then after that, here you learn transmission. So before you send the electricity, you have to do you have to go through step up transformer first, and your alternating current can work in a step up transformer. Then you send it to the city, you use step down transformer, the voltage back to low value, which is safer. But of course, the problem is heat loss will be greater. But the thing is, we are not going to travel for far distance anymore. So that will minimize the heat loss. Okay, so now when they reach housing area, the electricity reach housing area, they will go into your house until the socket. Okay, your house have plenty of socket, and then you have to use plug, and then you connect it to your electrical device like TV. Like maybe you want to charge your handphone. The problem is, most of the electrical device that we use, they cannot take alternating current, so they have to take direct current. Okay, so for example, why they cannot take? You imagine, alternating current. Let's say you are watching TV. Okay, you are watching TV. If you are using alternating current, so the problem is the TV may turn on and become very bright. After that, if you turn back to very dark, and then after that cannot work for a while because the current is in the opposite direction, then it's become dark, then it turn bright again, then become dark again. So it's not fun, right? If you watch TV which turn on and off like that. Okay, so that's why we have to design our circuit to make the alternating current that reach our house become direct current, so that our electrical device can work. Okay. Likewise, fan. Okay, never mind. Okay, so we don't want too many examples. Okay, how to change alternating current to direct current? The the basic is half wave rectification. Half wave rectification is where you keep the positive graph, negative graph, you cancel it. How you cancel it? You use one diode. The function of diode is to allow current flow in one direction. Allow current to flow in one direction. So this thing is diode. Okay, with an arrow there. So what happened then is you're using alternating current. So alternating current, when they flow, let's say initially they are positive. Okay, positive means they flow this way, let's say. And when they reach the diode, they can flow through it. Because you see the arrow is this way, right? That means current can flow this way. And then they pass through the electrical device. Then the electrical device is connected to voltmeter, right? So you can detect. Then they go back. Yeah. So after a while, it becomes negative. The moment when it becomes negative, right, that means the current will go from here and then stop. Stop because diode is there. It avoid the flowing of the current in the opposite way. So that's why when it's negative, the whole part disappear, blocked by the diode. Then after a while, it come back to positive. Positive means flow this way. Can happen. So that's why when it's positive, this part remain. When it's negative, cancel off because the diode is blocking. So it seems like we have solved the problem, but only solved 50%. Now we have a current that can only flow in this way. When they're opposite, then it will stop. It will stop. So the current can flow in one direction only. So, but still, it's not fun, you know. First, you block 50% of the current already. 50% gone already. When they are down here, gone, blocked already. And if you are watching TV, imagine turn on, then after that off for part of the time, and then turn on again, then turn off for part of the time. So it's not fun watching TV in that way. So we need a better design. So let's see. We design it in this way, which is called full wave rectification. So rectification is what? Rectification is actually the changing of the alternating current to direct current. Okay, so full wave rectification is we want to keep all the wave. We don't want to block 50% of the wave and remain 50%. So we want to keep all. So that's why just now it's half wave. Just now half wave because only half wave remain, another half is blocked. Now this is full wave. We want all the wave to be there. So we need to design our diode by using 4 diodes. In this particular arrangement, you need to memorize the arrangement. Okay, memorize the arrangement. So this one up, this one down, this one down, this one up. So memorize the arrangement. Okay. So how good is this arrangement? This arrangement is called bridge diode. bridge diode. So again, we are having alternating current. The current may come out from here at the beginning when it's positive, then they come out from here. Then the current reach the bridge diode. They cannot flow here because here the diode will block it. They can only flow here. Then they cannot flow here because the diode is blocking. So they have to flow and pass through the electrical device, which is called load. Pass through the electrical device and then come here. And then when they reach here again, so they can go up and down, right? Of course, they will go down. You know, electricity, they want to move one round and go back to the source. If they go up, right, they have to start again, you know. So they won't be so stupid to start again all the time, you know. So they will go down and then go back to the source. Okay, so they keep the positive wave. Now when it's negative, that means the current will flow from the different direction. They flow down, come here. When they reach here, they cannot go this side because blocking happened due to the diode. So they have to flow this way. When they reach here, they cannot flow this way because blocked by the diode. Then they flow here. And again, they are going down. You know, same with just now, no? Same with just now. Just now going down. Now it's going down again. So going down again, that means this load, right, experience the same direction. The experience current in the same direction, which is up to down. So that's why the reading is in the same direction as this one. Okay, up to down. Just now up to down also. Now up to down also. Now they flow and then they cross here. Okay, now when they reach here, right, they can go down. But the thing is, if they go down, they have to restart again. So they have to go up and go home. Okay, so when it is negative, then they manage to keep it and change it to the positive. And after that, this repeat again to get the third one. Then this one repeat again. And the fourth one, which is negative, become positive. So it seems like we managed to keep all the wave, and at the same time, we change all the wave to positive direction, which is up to down, same directions. This is quite perfect already. It seems like the alternating current has become current in one direction, which is direct current now. But the thing is, they are quite bumpy, you know. So if you're watching TV, they are still turning off for a while, and turn on again, and turn off for a while. The period is much more shorter already. It is a much better improvement compared to half wave. Okay, so we still need to do something to make it much better. So that's why we have the next page. So on this page, we have smoothing. What happened just now is after full wave rectification, our alternating current has become direct current that is bumpy, go up and down. That means they use the words bumpy direct current. Okay, so after full wave rectification, the outcome is bumpy direct current, which means they go up and down. So to avoid this problem, we had to go through smoothing in order to produce a steady direct current from bumpy direct current that result from the full wave rectification. So we need to use a smoothing capacitor. So we learn capacitor. Capacitor, the function is to store energy. Okay, it's to store energy. So let's see. This is the capacitor. This is your electrical device. Okay, you connect your electrical device with a capacitor, then smoothing happens. the capacitor will work in this way. The capacitor charges, they can store energy, right? So that means you charge the capacitor. When are you going to charge the capacitor? So it's written here. The capacitor charges and maintain the voltage as alternating current voltage rises. That means when they come up, the capacitor is charged. Okay, so I write here. This one I call it 2. Number 1 is where you charge the capacitor. Number 2 is where the alternating current is going down. The capacitor has been charged. Now it is time to discharge. Okay, so number 2 is where capacitor discharges. And then the process keep repeating. Now when they come out, then the capacitor is charged. Then capacitor discharge, making the voltage never decrease too much like before. Before they decrease a lot, So they decrease a little bit only until the capacitor no more charge, or not to say discharge until 0%. That discharge maybe let's say discharge 50%, then you charge it again, then discharge 50%, then charge again, discharge, and so on. So the outcome is it become very smooth already, much better already. Okay, so if you are watching TV, the TV is on all the time. Although they go down a little bit, your eyes may not be able to detect. Okay, because they just go down a little bit, not so detectable. Okay, so this is good enough. You make it smooth already. As the wave slopes downwards, the capacitor begins to discharge in order to maintain the voltage. So you manage to maintain it. Okay, so the thing is, capacitor has different kinds of capacitance. So should we use small capacitor with small capacitance, or should we use uh, a large capacitor with large capacitance? So we need to understand that also. What kind of capacitor that we should use here? Small capacitance or big capacitance? So they mention or they explain it here. A small capacitor discharges more rapidly. They discharge very fast. That means they can discharge and become 0% very fast. Release all their charges very fast. Okay? Then a large capacitor. Large capacitor, basically they have more energy stored. So they will take more time to discharge. Okay? And give rise to greater ripple in output. Greater ripple is like, okay, let's say I use blue color for small capacitor. Small capacitor, right? So you discharge it, and after that, the charge finish very fast. Then you discharge it, then the charge finish very fast, and so on. Finish very fast. Okay, that is finish very fast. If they finish very fast, right? So I label first. This is small capacitor. The charge finish very fast. and make the voltage go down quickly. The red one is large capacitor. So if you follow the blue one, what happened is there is a greater ripple. That means up and down is quite a lot. Up and down, quite a lot. Okay, so but if you are using a large capacitor that don't go down too much, so of course the red one is better lah. Okay, so the blue one not so good. They go down a lot. If the load resistor is small, load resistor mean the output. Okay, the capacitor will also discharge rapidly. So they are trying to talk about this. If this one has low resistance, then they will discharge quickly also because low resistance, right? So they can come out easily, because this is not blocking too much. Can come out easily, so they discharge rapidly also. Okay, so the capacitor will also discharge rapidly. Discharge rapidly means they are like the blue color, go down very fast. So the blue graph happens in two situations. The first situation is if you are using small capacitor with small capacitance, then they go down very fast. The second situation is when you use load with low resistance, then the capacitor discharge very fast also. Okay, so these are the two factors that make the discharge happens rapidly. Okay, so how to choose capacitor then? We have some calculation here. You have to take the capacitance of the capacitor, multiply with the resistance. Okay, so resistance, of course, the resistance of this thing, no? This electrical device. Take the capacitance, multiply with the resistance, then you get a time constant. Time constant. What is meant by time constant here? Let's think about it. We consider their unit alone, then you will understand something. C times R. The unit of C is farad. The unit of R is ohm. Then we know C equal to capacitance equal to charge over potential difference. The unit of this is coulomb. The unit of this is volt. Okay, so at the end, the farad become coulomb per volt. And how about resistance? Resistance, if you remember the formula, R equal to V over I. The unit for V is volt. The unit for this is ampere. So it becomes V over ampere. And imagine these two multiplying. And because of that, we can cut the volt away. So left up with coulomb multiplied with ampere, -1. Okay, so I write down first. End up with coulomb multiplied with ampere, -1. Then we also need to know that I equal to QT. I equal to QT. So that means the unit ampere equal to coulomb multiplied with time. Oh no. Is it like that? Q over T. the other way around. How fast the charge move. Current is how fast the charge move. So Q over T. So the unit is Coulomb over time. Okay, so ampere is Coulomb over time. Second. Ampere negative 1 is C minus 1 S. Okay, then I put it back. Coulomb time Coulomb negative 1 S. Then you can cut the Coulomb away. End up with S. So by considering the unit alone, we understand something. When you take capacitance multiply with resistance, you get something in the unit of second. So this is time, it's time. So that's why it's capacitance times resistance, you get a time. So you get what kind of time, you get the time, this time, right? The time that you get here is the time taken for the capacitor to discharge until it is 1 over E of their original value. Okay, the charge to fall into 1 over E times of the original charge. So with this time constant, then we can decide. Okay, we can decide something like this. If the CR is big, then it will take a longer time for it to discharge to 1 over E of the original value. If CR is big, it takes longer time to discharge, in other words. So that's why we have to use large capacitor. Large capacitor has greater CR. C is big, capacitance is great. R is also, R depends on this basically. Okay, so C, if you are using large capacitor, so the CR will be big because of the big C. Okay, then it takes longer time to discharge. So it will follow the red color graph. Discharge slowly. Before it finish discharge, you're already recharging, So that is the best thing. The graph won't be too ripple like the blue one. So that's why when you count your CR, right, once you get the answer, you can just compare with the period. Compare the period. Period is the time when they move one round, right? Okay. The CR value, right, should be much greater than the time period of the alternating current supply. So capacitor does not have sufficient time to discharge significantly. That means we don't want the blue color graph to happen, where the discharge a lot, and making the output like very bumpy. So we don't want that. And to avoid this, we have to use large CR. The design must be large CR. This R must be big enough, this C must be big enough, and then it will follow the red graph. If the R is small, this will be small, CR will be small. CR small means that we discharge very fast, where they mention here. When the R is small, CR is small, capacitor will also discharge rapidly. So this one matches with what we discussed just now. Okay. In general, the greater the value of CR, now they purposely turn the other way around, R times C. R times C is CR. The smoother the rectified AC, alternating current. Okay, so we finish up the theory already. let's see how they ask in exam.